Okay, as we enter the second half of the course, we're going to need a few theorems which some of the results from the second half rely on. So let's take one lesson here and just go through a lot of different theorems that we've talked about a little bit before, but we'll kind of bring them back and pull them all together. And there was a little technical difficulty when I tried this the first time, so I've got my notes up and going to splice a couple things together. So anyway, here recall is the definition for a function to be continuous. A function is continuous if whatever the limit is for a particular function at a point, here's the point x right there. Recall that as you approach x, this right here is the limit, and the value of the function might be up there. There's nothing that says that the limit has to be equal to the value, but if indeed they are the same, if indeed the value of the function is equal to the limit, then it's said to be continuous at that point. And if it's continuous at all the points in a particular interval, then we say it's continuous on that whole interval. If it's continuous on everything in the whole domain of a function, then we say it's a continuous function. So that's the reminder of what it means to be continuous. What does it mean to be differentiable? Well, to be differentiable, of course, means that the derivative exists at a particular point. To be differentiable at x means that the derivative exists, which means that this limit exists, which means graphically that if you are at a point x right here and you move away so that this is the point t, and you look at the slopes of the secant lines, this should start getting boring to you now, the number of times I've said it, but you basically do what? You push t into x, and as t goes into x, two things happen. This gets smaller and smaller, and this gets smaller and smaller. And they both go to zero, and it's really the ratio at which they go to zero which is your derivative. You just think of a straight line. If you have a straight line like this with slope 3, then as you push this value into this one, the slope is always going to be 3, 3, 3 all the way down. No matter how close you get, that ratio is always 3. So that's really what we're doing, is we're saying what's happening to that ratio. They're both going to 0, but it's the ratio at which they approach 0. So anyway, that's what it means to be differentiable. Do you also recall the things that are not differentiable? Here, for example, the absolute value function was not differentiable at 0 because everywhere else along here the slope was 1 or -1, and it had a unique tangent line. The tangent line was, in this case, the function itself. But at 0, there's not a unique tangent line. There's all sorts of different lines that could hit that thing right at that sharp corner. And because of that, if you try to evaluate this limit at this point, you'll see that the slope is always 1 as you approach from one direction, and the slope is always -1 as you approach from the negative direction. And so this quantity here has no limit. It's 1 coming here, -1 coming here. So as the picture shows, this thing here has no limit, even though the function itself does have a limit. The function's going to 0, but the derivative is 1 or -1. Okay, so that's what it means to be differentiable. And another thing that I mentioned just briefly, but I want to talk about a little bit more again, is that if a function is differentiable at a value x, then it's continuous there. And you can see that both from the definitions and from a picture. Let's look at the definitions first. In order for this limit to exist, notice that as t approaches x, the bottom is going to go to 0. So in order for this thing to exist as a limit, the top has no choice but to go to 0. If it went to anything but 0, you're going to get something over 0 which is going to go off to infinity or whatever, okay? So if this limit is going to exist, they both have to go to 0. But notice, if they both go to 0, then what are you concluding? You're concluding that the limit as t approaches x of f of t has to be getting closer to f of x. For this to go to 0 means f of t has to be approaching f of x, which is exactly what it means to be continuous. See that? So if it is differentiable, then for sure it's continuous. Another way of thinking of it by way of a picture is that if you have something like this, and you want the derivative at this point, let's even make it easier. So kind of see, like so, and say it's up here. Okay, so then what happens as you take the limit of this quantity? Here's x right there. Here's t right here. So here's f of t. Here's f of x. And so notice what's happening. As t gets closer and closer to x, this quantity gets smaller and smaller, but f of t is heading down there, so f of t minus f of x is always going to be this large quantity. It's not going to 0 in this case. See that? So there's why if a function is not continuous, there's no way it can be differentiable. Okay, very good. So so then here's something, a quick lesson in logic that you might be new to you. Okay, quick lesson. If in Detroit, then in Michigan. I think there's only one Detroit in the world, and that's in the eastern side of Michigan. So this is a statement, and this statement is true. Agreed? If someone's in Detroit, then they're in Michigan. If you switch the if and the then around, if in Michigan, then in Detroit, then that's obviously not true. A person can be in Michigan and not be in Detroit. So that's false. That's called the converse. The converse may be true, but it doesn't follow from the statement. It has to be proved separately. Okay? Then, I think it's called the inverse, is what you get by putting a not in front of each thing here. So if not in Detroit, then not in Michigan. Notice that's also false. A person cannot be in Detroit, but they might still be in Michigan. So that's false. But finally, if you do both of these things, you switch the if and the then around, and you also put a not in front of each one, you get what's called the contrapositive. If not in Michigan, then not in Detroit. And notice that's called the contrapositive. Notice that that is true. That's logically equivalent to the original statement. If you're not in Michigan, you're not in Detroit. So that's true because it's logically equivalent to this. So that's kind of nice. That's a nice little bit of logic to know. And I've used that right here. What do we say here? If f is differentiable at x, then it's continuous. So it's equivalent to say if it is not continuous, then it is not differentiable. Okay, if it's not continuous, then it's not differentiable. So either way, it's kind of nice sometimes to see it in either expression. So now, with all that as a background, let's look at our new theorems. Intermediate value theorem. The intermediate value theorem says something kind of obvious. Okay? It says that if you have a function that, say, has this value to it, so here's a, and say here's f of a right there, and say here's b, and here's f of b right there, then it says if you choose any point between f of a and f of b, let's just choose some point there, call it p, and you draw the graph between these two functions, or I'm sorry, between these 2 points, this graph has to at some point cross this line. In other words, the value of the function somewhere between a and b has to be equal to p. Now, it's not always true. You could have a function like this. Agreed? That's a perfectly good function defined on the interval from a to b, which doesn't ever cross that line. But the point is, I had to resort to a function which was not continuous, a discontinuous function. If you do have a continuous function, you have no choice. You've got to cross that line. It's got to cross somewhere or another, okay? Could be like that. It doesn't say how many times it crosses. It could cross them a bunch of times. It could cross, let's get one that crosses 3 times. 1, 2, 3 times. Is it possible to cross 4 times? I think so. Let's try it. That's an even number. So it could go 1, 2, 3, come down and just touch it. 4, like that. So basically, any number of times you could cross it, but the intermediate value theorem says at least once. So given any p, there's some c down here which gets sent to p. Okay? So this is an important theorem in its own right. Here's just one example of how this is so kind of interesting. Consider the globe. Okay, and consider the equator of the globe right here. Would you agree with me that the temperature, if you were to take a snapshot right now of the temperature at every point along the globe, along the equator, that temperature is a continuous function, right? There's no places along the equator, even if it passes through a volcano or someone's kitchen or whatever else. There's no place where the temperature is ever going to take a quick break. If you're going from the outside of an oven to the inside of an oven, if that happens to be on the equator, it might be that the temperature goes up really, really fast, but it'll still go like this as it goes through the door of the oven. It'll never actually be a break like that. So here's the question. Is it the case, excuse me, that there are 2 points on the equator diametrically opposite each other? That means on the diameter of the globe goes right through the center of the earth and going from one to another, that have exactly the same temperature. Is it always going to be the case that there's going to be 2 points diametrically opposite that have the same temperature? No matter how the temperature might be, whatever might be happening in storms and everything along that time, but it's taken a snapshot. And the answer, surprisingly, is that there will be. And here's the way you can prove it, and it uses the intermediate value theorem. You start like this. You say, here's my left hand, and here's my right hand right here, and I'm going to take the difference in these 2 temperatures, this value right here minus that value. If this value and this value happen to be the same, then the difference of those values would be 0. Okay? If they're not the same, let's suppose that it's hotter, that this one here is hotter. So the difference from here to here is going to be some positive number. And now here's what we do. We move around the equator like this, always keeping these things diametrically opposite and always taking the difference in temperature. Okay? It might go up like this. But here's the point. By the time I get to this configuration, now I'm always taking this one minus this one. So now this temperature minus this temperature is going to be negative. So by the time you get to this configuration, now the temperature will be negative, and it started off positive. And since we assume that the temperature is continuous, there's going to be at least some spot where you cross 0. And by crossing 0, you mean that those 2 temperatures are the same. So I think it's a really cool example of how the intermediate value theorem can be used to prove something true which isn't at all obvious. It's reasonable, but it's not at all obvious. Okay, so that's that. Next theorem is called the extreme value theorem. And the extreme value theorem says this. It says if you've got some continuous function on a closed interval, so from here to here, then the maximum value and the minimum value of that function, first of all, they're going to exist. Now you say, of course the max and the min are going to exist. Well, if it's not continuous on a closed interval, look what can happen. You can have a function like this, which goes up to infinity on the open interval from 0 to 1, say. So there's no maximum value. Or you could even have a function like this. Doesn't have to be that weird. It can be just the function from here to here on the open interval from, say, 1 to 5. And it never hits this value and it never hits this value, so there's no max and there's no min, but it is nice, but it is continuous on the open interval, but not on a closed interval. So a function doesn't necessarily have a maximum or a minimum, but if you have a continuous function on a closed interval, then you're always going to have a max and a min. And you say, well, why does it have to be continuous? Well, if it weren't continuous, you could have a function like this. Here's a closed interval, and the function could go up like this, and then like so, and here's the value there, and something like this. And so it never quite hits this value, and it never quite hits this value, so there's no max and there's no min, and so those don't exist. So you need two things. You need a continuous function on a closed interval. And so you'll always have a max or min. It looks like in this particular case, the maximum occurs right there. And it looks like the minimum occurs, I guess I didn't, maybe I'll make it a little more obvious. I'm going to make this one come down a little bit more. The minimum occurs right there. Okay, so there's the minimum. So then, that's important, because quite often with functions, you want to know whether there's a max or a min. If you're looking for a profit or something like that, you're often looking at either the largest profit or the lowest expense or something like that. So then, once you know that they do exist, then the question is, where might they occur? And just as this picture indicates, candidates for where they might occur are either the endpoints, so you need to check them out, and also places, do you see what's going on here? Places right here where it looks like the derivative is 0. Do you agree? The derivative is 0 there because it flattens out. And so right there, the derivative is 0. And so that's another place where the max or the min might occur. So let's just say this. Where will max and min occur? One place is the endpoints. Second place is where the derivative, I'll just use where the derivative is equal to 0. So those are places you need to check. Does that take care of it? Or are there any other possibilities where the derivative might be 0? Well, let me remind you that here is a function where the derivative exists right here. There's a unique tangent line right there. That's a spot where the derivative is 0. But right here, the derivative doesn't even exist. Notice there's no unique tangent line. There's all sorts of things that touch it just at that one spot. If you were to evaluate this limit of this function at this spot right here, this limit would not exist. So here's a spot where this function doesn't have a derivative, and you can tell because there's that sharp corner there that it's not differentiable there, the derivative doesn't exist. But notice that that is a place where you might have a minimum, because indeed that is the minimum value of this function. So there's the third candidate. It's a place where f prime of c doesn't exist. In other words, where the function is not differentiable. Okay? So these are two critical places to check for a function. Not only the endpoints, but it's critical that you check here and also critical that you check there. And that's why we call those two kinds of points, I just gave you a clue, critical points. Critical points are places where the derivative is either 0 or where it doesn't exist. And so those are going to be important coming up in the future. So that's the extreme value theorem. Okay? Finally, the last one is called the mean value theorem. Mean as in average. Mean value theorem. Sometimes we say for derivatives. Okay? And here's what the mean value theorem says. It says if you have a function, say that goes through this point right here and this point right here, which is continuous and which is differentiable on this interval, which means that it not only doesn't have any breaks, but it also doesn't have any sharp corners, then if you draw that function and you draw this line right here, which goes from that point to that point, let's say that this is A right here and this is B right there, and you find the slope of that line. What is the slope of that line? That's easy enough to get. It's f of b minus f of a all over b minus a. Agreed? There's the slope. And you can think of that as the average slope of this function from here to here, right? Because at some points the slope's going up faster than that. Other times the slope doesn't have as high of a slope as that. But you'd say, oh, it's kind of like if two people were walking up a hill from here to here, and one person were to take this track and one person were to take this track. On average, they went up at the same rate. This person just kept the same rate going the entire time. This person had to climb hard for a little bit and then got a break and then had to climb hard again. But the average rate was the same because their ending and beginning altitude was the same. So it's called the mean value theorem. And anyway, what the mean value theorem says is, whatever that average value is, that if this function is differentiable inside this interval, that average value has to occur someplace. And you can spot it pretty easily just by looking at this right there. There, whoops, and right there are two places where this function has a slope which is equal to that average slope. And again, the mean value theorem doesn't say that there's just one or anything else. Here would be a function like this, for example, which would have only one place that has that average value. You could have a function like this, which would have a whole bunch of places. 1, 2, 3, 4, 5, 6 of them. Okay? But the mean value theorem says at least once. At least once. And again, I'm claiming that this is only holds to be true for sure if you have a function that has a derivative everywhere. Did you see why? If it doesn't, otherwise you could have a function that looks like this. See that? It's a nice continuous function, no problem with that, but there's no place on this whole interval where this function takes on this average value. And there's no guarantee that it should, because this function is not differentiable right there. There's no derivative right there. So that's called the mean value theorem. Okay? The mean value theorem, I'm going to write that one down just because it's a little more important than the others. So I'm just going to say on AB, f is differentiable. If it's differentiable, then we know it's continuous. Then there is a point C between A and B for which what? We first take this average slope, and once we have that average slope, we know there's some point between A and B where the derivative at that point is equal to that average slope. Okay? And here's why this one is so important. Okay? This one's going to be especially important for things we do in the next few lessons. Here's why. We know that if you have a function which is a constant, we know that the derivative of that function is 0. Okay, you can use the definition, and you're going to get 0 or k minus k up on top, and so the limit's going to be 0. So no problem. But what we haven't thought about yet is this. It's the converse. Remember what the converse is? So if, then. What if we switch them around? If f prime of x is equal to 0, then f of x is equal to a constant. If the derivative is 0 on a whole interval, then does that mean that that function has to be a constant? Okay, there's no guarantee from a contrapositive, because I'm switching the if and the then around, so there's no guarantee that this is right. It still might be right, but if so, we have to prove it. And it turns out we can prove it. And we can prove it with the mean value theorem. Because, let's just look at it. If you have an interval like this, and you have an A right here and a B right there, and what does it mean? Let's just be clear. Suppose this is my interval from here to here. And I just choose any 2 points inside. Call them A and B. Okay, any 2 points. And so it's differentiable from A to B in particular. So the question is, to be constant means that the value of the function at any 2 points has always got to be the same. That's what it means to be constant. At any 2 points, it's got to be the same. And we see that it has to be because, look, f of b minus f of a over b minus a is equal to the derivative at c, where c is something in between. But if the derivative is always 0, then this quantity is always going to be 0, and the only way this can be 0 is if f of b is equal to f of a. So sure enough, if the derivative is equal to 0 everywhere, then f is a constant. That's very important. Equally important, if you have the difference between 2 functions, and you take its derivative, and if its derivative is 0, then we know how to take the derivative of the difference of 2 functions. Anyway, if the derivative of this is 0, then what did we just prove? Then this function here has to be a constant. Okay, so let me say it again. For any old function, if the derivative is 0, then this function is a constant. So since the derivative of this function is 0, this function has to be a constant. And if that function is a constant, that means that f of x is just equal to g of x plus k. That's a very important proof, because what that is saying is that if you have any 2 functions and you take the derivative and those 2 derivatives end up being equal to each other, then those 2 original functions have to have the exact same formula, except for the fact that there might be a constant on one. So let me just let's see. I guess I'm going to have to erase this. Sorry about that. But what that means is that if you have some function like this, let's say f of x is equal to something really weird, e to the sine of x cubed all over ln of x, and you took its derivative, and you got its derivative, okay? The question is there some other formula which, by the time you're all done, could end up giving you the same derivative? I'll call this one g. Some totally different formula here, but the derivative ends up being the same. Is that possible? And the answer is no. What we just proved is that if anything else gives you the same derivative as this one, how do these 2 functions differ? This one has to look exactly the same, except maybe you've got a 5 attached on the end. Okay? So there you go. So that's good for the present. There's a whole bunch of important theorems that will come to our aid. Good.